Imagine a single server rack generating so much heat that the cooling fans alone draw enough power to run a small house.
It is honestly wild to think about.
Right. I mean, that is the secret of crisis happening inside AI data centers right now.
Yeah.
And the crazy part is the culprit isn't the multi-million-dollar GPUs.
No, it's really not.
It isn't the massive switch ASICs either. It is literally the physical cables plugging them all together.
Yeah, the cables.
So for you listening today, our mission on this deep dive is to look under the hood of these massive AI clusters. We want to explore why optical interconnects have suddenly become, the defining architectural bottleneck of modern computing.
Because we are essentially hitting a wall with basic physics here.
Yeah.
Pushing data at 800 gigabits per second, it breaks a lot of the traditional assumptions we've relied on for, the past decade of data center design.
Totally. And we are pulling our insights today from a brilliant, highly technical engineering deep dive published by Axiom. It was authored by Dr. Carlos Berto, who is their director of network engineering.
It's a great piece.
It really is.
Yeah.
And the core reality he lays out is startling. He basically says that at 800G, picking an optical transceiver is no longer a simple component purchase. You don't just open a catalog and buy a cable anymore.
Not at all. It has escalated into a fully coupled, system-level design decision.
Right.
You are forced into a corner where you have to balance two completely opposing, incredibly painful extremes.
Which is always a fun place for engineers to be, right?
Oh, absolutely. On one hand, you have crippling thermal loads at the front panel of your switches.
Okay.
And on the other hand, you have these massive, sprawling operational failure domains that will absolutely destroy your MPTR, your mean time to recovery.
Wow.
Yeah, it'll keep your operations teams chasing ghosts for weeks.
Okay, let's unpack this. Let's look at the two specific technologies sitting at the center of this crossroads.
Sure.
On one side, we have DSP-based optics or retimed pluggables, which rely heavily on an onboard digital signal processing.
Or the DSP.
And then on the other side, we have LPO, which is linear pluggable optics. And that approach strips all of that DSP stuff out.
Exactly. And to understand why these two are fighting for dominance, we have to look at the mechanism of what actually happens to a signal at 800G.
Like physically on the wire.
Yes. When you are pushing that much bandwidth over a copper trace or through a fiber, the signal naturally smears and echoes.
It gets messy.
Very messy. You are dealing with intense crosstalk, insertion loss, and signal reflection. In engineering terms, the eye diagram of that signal essentially closes up.
Okay, so where does the DSP come in?
So the DSP inside a retimed module acts like active noise cancellation for light.
Oh, I like that.
Yeah, it is actively doing heavy real-time mathematical equalization to subtract that noise. It reopens the eye and cleans up the signal completely before it hands it off.
Which brings me to an analogy I was thinking about. Buying a DSP module is basically like buying a fully tuned top-tier luxury car.
Okay, yeah.
Right. It has this advanced onboard computer that dynamically handles every single bump in the road.
Right. It does the work for you.
Exactly. It monitors the terrain, adjusts the active suspension, and delivers a perfectly smooth ride, regardless of how degraded the actual pavement is. You just get in and drive.
I love that analogy.
Thanks. But going with LPO, because you rip that DSP out entirely, it's like buying a raw, stripped-down racing engine.
Yes. Very lightweight.
Incredibly lightweight.
Right.
But there is zero onboard computer doing the equalization for you. So you have to manually tune the suspension, the steering, and the chassis yourself to make sure that raw input doesn't just, rattle the whole vehicle apart.
What's fascinating here is how perfectly that captures the burden of physical optimization.
Yeah.
With LPO, you remove the active noise cancellation. You are relying on simpler analog linear components.
Okay.
Which means you're pushing all of that complex signal correction work back onto the host server's SerDes. We are suddenly trying to optimize competing constraints here.
Right, because you want the lowest possible power draw, I imagine.
Exactly. We want low power, but we still have to manage incredibly tight safety margins across the entire optical channel.
Okay, so taking that heavy onboard computer out of our luxury car obviously saves weight. In the data center, stripping out the DSP saves power.
Right.
So if the fundamental trade-off here is between managing heat and managing failure domains, let's look at the heat first.
Let's do it.
Why does the power consumption at the very edge of the network switch the front panel, right? Why does that dictate the architecture of the whole room?
Well, Dr. Berto shares some steady-state lab results from Axiom that really highlight the severity of this problem.
Okay, what were the numbers?
When they tested 800G OSF key modules, The LPO version averaged about 8 watts of power consumption per module.
8 watts.
Yes. And the DSP-based version, the one running that heavy mathematical equalization, averaged around 16 watts.
Wait, I am looking at these numbers, and I have to push back a little here.
Well, go for it.
We are talking about an 8-watt delta per module. I mean, an 8-watt LED barely lights up a hallway.
True.
In a hyperscale AI data center drawing tens of megawatts, where a single GPU tray can pull kilowatts of power, why should you, or any facility engineer, lose sleep over 8 watts?
It sounds trivial, right? But it's because of localized physical density.
What do you mean?
Those 8 watts aren't spread out over a massive silicon die with a giant cold plate attached to it. They're acting as a severe localized bottleneck.
Oh, I see.
If we run the rack-level math from the Axiom piece, imagine a single switch tray packed with 64 of these 800G ports.
Okay, 64 ports.
If you populate that with DSP modules instead of LPO, you are adding 512 watts of pure heat.
Wow, just sitting right there on the metal faceplate.
Exactly. That is over 1,700 extra BTUs per hour, localized to a few square inches of front panel real estate.
That sounds like a nightmare to cool.
It is. The front panel of the switch is arguably the worst possible place to try and dissipate heat. You have an absolute physical limit on your fin volume.
Right, because the heat sinks can only be so tall before they block the port above them.
Precisely. And the cages themselves severely restrict airflow into the chassis.
So it isn't about the power bill for the facility at all.
No, not really.
It is about the fact that you have a tiny, highly concentrated surface area turning into a localized oven, and you literally just run out of mechanical headroom to cool it.
Yes. And this introduces what the article identifies as the non-obvious kicker.
Which is?
Fan power amplification. To cool that front panel oven, the system is forced to spin its cooling fans much, much faster.
Okay.
And fan power usage does not scale linearly. It follows the affinity laws of fluid dynamics.
Oh boy, fluid dynamics.
I know. But it just means the power required scales roughly with the cube of the fan speed.
The cube.
Right.
Yeah. If you need a fan to spin 20% faster to push air through those dense optical cages, the power draw of that fan spikes by over 70%. Are you kidding?
Yeah.
You are telling me that by adding 8 watts of heat at the module level, you are forcing the host switch to consume exponentially more power just to spin the fans hard enough to stop the silicon inside from melting down.
That is the exact mechanism. You completely erode your acoustic headroom and your thermal margin.
That is insane.
And it gets worse. Axiom also highlights thermal sensitivity, which is the watts per degree Celsius slope.
What does that measure?
It measures how aggressively a module's power consumption drifts as the ambient temperature rises.
Oh, so it's a feedback loop.
Exactly. DSP modules can exhibit higher thermal sensitivity. So if the data center aisle gets a few degrees warmer, the module draws more power.
Which creates more heat.
Right, creating more heat and forcing the fans into an even steeper, more dangerous point on that cubic power curve.
Wow.
LPO breaks that vicious cycle entirely because it runs inherently cooler from the start.
Okay, so looking purely at the thermal physics, LPO is the indisputable winner.
Hands down.
It keeps the fans quiet, it stops the cubic power spikes, and it keeps the front panel from turning into a stovetop.
Yep.
Which leads to the obvious question. If LPO saves you from all of that thermal nightmare, why wouldn't every single architect use it exclusively? Where's the catch?
The catch is the failure domain.
Ah.
This is where the engineering reality of stripping out the DSP really bites back. We established earlier that the DSP module acts as a very strong demarcation point.
Right, the active noise cancellation.
Exactly. Because it actively cleans up the signal, it absorbs all the channel impairments inside its own casing.
Okay, so it isolates the problem.
Yes. If an optical link starts taking on errors, the troubleshooting process is beautifully simple. You rip the module out and slot a new one in.
So the failure domain is contained strictly within the physical boundaries of that one pluggable device.
Exactly.
Here's where it gets really interesting. Because if we go back to our analogies from earlier, relying on DSP optics is essentially like staying at an all-inclusive resort.
Okay, I'm following.
If the air conditioning breaks in your room, you don't care how the HVAC system is routed through the building. You call the front desk, the resort staff handles it entirely within their walls, and your problem is solved.
Right, not your problem.
But using LPO is like renting an Airbnb.
Oh, no.
Yeah. If the shower stops working, you are suddenly dropped into an investigative nightmare. Is it the internal plumbing of the house? Is it a drop in pressure from the city water line? Or is the shower head itself just calcified?
You have absolutely no idea.
Right. And you have to investigate the entire chain to find the root cause.
That is spot on. Because LPO removes that active noise cancellation, the system boundary completely dissolves.
The module is no longer taking care of itself.
Exactly. The performance of that link suddenly becomes this fragile, unretimed concatenation of multiple distinct elements.
Like what?
It is the host server's SERDES, plus the exact impeders of the PCB traces, plus the physical mating of the connectors, plus the linear optics themselves.
So you are stringing all of these analog variables together into one long, highly sensitive chain.
Yes.
And forcing the host SerDes to basically shout louder and listen harder to make sense of the signal.
That's a great way to put it. And this introduces severe port-to-port variability.
Really, even on the same switch?
Even on the exact same network switch, two physically identical ports can behave completely differently.
Wow.
One port might work flawlessly, while the port right next to it drops massive amounts of data.
Why? Just because of manufacturing tolerances?
Exactly. Microscopic manufacturing tolerances in the metal cage, or maybe a slight temperature gradient across the ASIC, pushing the PCB impedance out of spec.
That sounds awful to fix.
It is. The debug process stops being a simple component swap and morphs into highly complex channel engineering.
Which means you are no longer just sending a technician down the aisle with a fresh module in their hand.
No, definitely.
You are suddenly acting as a forensic detective, trying to figure out which of those 5 different analog variables is generating the crosstalk.
And this raises an important question about how this technology actually scales.
Right.
Because we aren't talking about debugging a handful of connections in a lab. Modern AI fabrics consist of thousands upon thousands of interconnected GPUs.
Exactly. If you are dealing with a cluster of, say, 32,000 GPUs, does the power savings of LPO actually outweigh the massive operational drag of this complex troubleshooting?
That is the million-dollar question.
Because I know there is also a latency argument floating around out there too. A lot of the marketing around LPO claims it is superior for AI simply because removing the DSP removes the processing time, getting your data across the wire faster.
Right, the latency claim. Well, LPO does mathematically reduce the transceiver's internal latency because the signal doesn't have to pause to be digitally processed.
Okay, so it is faster.
Technically, yes. However, Dr. Berto provides a very necessary reality check on this in the Axiom piece.
What's the reality?
In almost all production AI fabrics, the end-to-end latency of a workload is not bottlenecked by the nanoseconds saved inside the optics.
It's not.
No. The latency is overwhelmingly dominated by the serialization and deserialization processes, the switch ASIC pipelines, and the software stack itself.
Oh, I see.
So while the LPO latency win is real on paper, it is highly situational and rarely translates to a meaningful acceleration of the actual AI application.
Okay, so if the latency benefits are mostly overshadowed by the switch pipeline anyway,
Yeah.
you are taking on all this analog complexity entirely just to save front panel heat.
Very much.
So does the LPO basically force you to turn your standard IT staff into dedicated PhD-level channel engineers just to keep the cluster from throwing errors?
If we connect this to the bigger picture, the answer is often yes. And that is why the failure domain is considered the ultimate cost center at cluster scale.
Interesting.
It defines your operational blast radius.
The operational blast radius, that is the perfect way to describe it.
It dictates the exact fallout of a degraded link. With DSP, the blast radius is microscopic.
You isolate the bad port, swap the module, and your MTTR is measured in minutes.
Exactly. But with LPO, a degraded link expands the blast radius across multiple engineering teams.
Oh, I could see that.
You get trapped in these cross-team escalation loops. The optics vendor says their module is fine.
Right.
The switch vendor says their cage is in spec. The server team says their SerDes is tuned correctly.
So everyone is pointing fingers.
Exactly. You end up chasing intermittent bugs and impossible to reproduce errors because the fault only exists when all those specific components interact at a specific temperature.
That sounds miserable.
It is. Smaller failure domains mean fast isolation. Larger domains mean sleepless nights for your operations teams.
You essentially save a few hundred watts on the front panel, but you spend all of those operational savings paying an entire team of senior engineers to spend weeks pointing fingers at each other.
Which is why selecting between LPO and DSP isn't just about reading a spec sheet.
It's way deeper.
It requires a highly disciplined, systemic deployment strategy. Dr. Berto lays out a very rigorous set of criteria for when an architect should actually deploy each technology.
So what does this all mean for the people actually building these data centers?
Well,
Because if the operational blast radius of LPO is this massive and sprawling, it sounds completely unscalable. You would only ever use this if you were absolutely forced to by hard thermal limits, right?
right.
And even then, it seems like you would need complete dictatorial control over your hardware vendors so nothing conflicts.
That is the exact conclusion of the deployment playbook.
Really?
Yeah. LPO is the correct choice when you are strictly limited by front panel thermals and you are operating within a tightly controlled, homogeneous ecosystem.
Okay, so no mixing and matching.
Exactly. You need a single switch platform, strictly enforced cabling rules, and a heavily constrained set of vendors. You use it for short-reach scale-out connections, where you can actively engineer your failure domain down.
That makes sense.
You have to standardize your cables and perform rigorous systemic temperature sweeps to characterize exactly how your specific hardware behaves under stress before you deploy it.
So you only run the raw race car engine if you own the entire racetrack, control the weather, and employ the pit crew.
That is a perfect summary.
So when do we deploy DSP then?
DSP remains the safer default architecture for heterogeneous environments.
Okay.
Long-reach connections, or any deployment where you expect multi-vendor optics and frequent recabling. If your ultimate goal is optimizing for MTTR and maintaining your operational sanity over saving absolute watts, you deploy DSP.
That seems like the logical choice for most people.
It often is, but the playbook notes that if you use DSP, you cannot waste the observability it offers.
What do you mean?
You must standardize how you collect module telemetry, integrate those error counters into your automated orchestration systems, and leverage the onboard loopback diagnostic.
Oh, to instantly isolate whether an error is happening in the fiber, the host, or the module itself.
Precisely. You have the data, so use it.
The final lesson distilled from all this engineering data is essentially a balance of currencies.
Oh.
Well, LPO buys you watts and critical cooling headroom, which the physics of dense AI architectures absolutely requires.
Right.
But DSP buys you isolation and robustness, which preserves human sanity and uptime.
Very well said.
The true cost of an optical link is not the bill of materials. The true cost is the operational reality your team faces when signal margins get incredibly tight across tens of thousands of ports.
It really exposes the delicate physical ecosystem underlying all these massive computational leaps.
It really does.
Behind every new large language model is a deeply complex web of analog links. And the engineers in the trenches are constantly walking a tightrope between the literal heat of the silicon and the operational survival of the network.
We've spent this entire deep dive agonizing over the physical and operational nightmares of pushing 800 gigabits per second.
That's a lot.
But the 1.6 terabit standard is already on the horizon.
Oh, yeah.
If 800G is currently pushing us to the absolute brink of melting faceplates or breaking our IT teams with cross-team escalation loops, 1.6T might require us to rip up the data center and redesign it from the concrete up.
That is a very real possibility.
The optical cables are no longer just connecting the architecture, they are dictating the physical blueprints of the entire facility. It is definitely something to keep in mind for you listeners the next time you see an AI generate a complex response in 3 seconds.
The physical infrastructure will always dictate the ceiling of our digital ambitions.
Thank you for joining us on this deep dive. Keep questioning how the invisible layers of our world actually work. Stay curious and keep exploring the hidden architecture of the tech world. We will catch you next time.